Hello Math 152 students. In this video, we'll take a look at a recap of 8.1 and then move on to the points in 8.2. So from our simulation, we learned that regardless of our underlying population, the distribution of our sample mean becomes normal as the sample size increases. We looked at samples of size 2, 5, 10, and then 30. And really, once we got to 5, 10, and 30 in our example, we had a pretty smooth curve. In general, for sample sizes greater than or equal to 30, we assume normality for the distribution of the sample mean. Now, in practice, you usually only take one sample, but you assume the distribution is normal under these conditions. Less than 30, we had two cases. If the underlying population is normal, the sample distribution of the sample mean is normal, regardless of if you had a small sample size or a large sample size. Then, if you don't know anything about the underlying distribution, you have to check your box plot and QQ plot. So for the QQ plot, we want to see that look approximately linear and nothing kind of too far away from that regression fit line. And for the box plot, we want to see no outliers. So if all of that checks out, we can use the normal curve, and then we can take our problem to StatCrunch to start calculating probabilities. Big point is, what can we do with normally distributed data? A whole lot. We can use StatCrunch specifically, but then we're going to be able to use inference methods based on a normal curve to create confidence intervals and then do hypothesis testing in later chapters. So we're going to see these conditions again and again in our next chapters. So what do we need to use that normal curve? A mean and a standard deviation. And what we saw is we had two formulas, one that gave our standard deviation, that said our standard deviation for our sample mean shrinks as n gets bigger, and then the formula for the mean tells us the mean of our x bar is the same as the mean of our underlying distribution. Okay, so let's take a look at our next slides. Our section 8.2 deals with another distribution, but this time we're going to be looking at the sample proportion. Things in 8.2 are going to feel similar and sound similar to some of our 6.2 problems with the binomial distribution. So what we want to do is kind of compare and contrast as we go along, see what's different in chapter 8 and what things we're using out of chapter 6. So let's suppose you wanted to know what proportion of individuals in a population have a certain characteristic. Could be something like owning a dog, supporting some sort of political bill, have a tattoo, really anything. Kind of like with the sample means, we consider whether or not it makes sense to survey the entire population. And almost always the answer is no. Time consuming, just resource restrictions, we would prefer to obtain a sample and then make inference based on our sample. So rather than surveying the entire population, we survey a sample and talk about the sample proportion. So the sample proportion is called p hat. You just have a p with a up arrow over it. And then based on our p hat, we can hopefully do some more stuff with it. So how do we calculate this p hat? Here, this formula tells us something we already know how to do. It tells us that if you have your sample size and your number of individuals with a specified characteristic, you can quickly turn that into a proportion by dividing. So we'll see an example in just a second. But we want to point out that this p hat is a statistic, meaning it's one number that estimates the population proportion. And if I take another sample, I could get another number. It might change from sample to sample, just like those average salaries changed if you collected a sample and the average salary, your friend did the same thing. So let's go on to our next slide. Sometimes we'll call this p hat a point estimate, meaning it's a single point that gives us an estimate. So let's go ahead and look at an example. In a university poll collected in May of 2008, 1,745 registered voters nationwide were asked whether they approved of the way George W. Bush was handling the economy. 349 said yes. Obtain a point estimate for the proportion of registered voters who approved the way George Bush was handling the economy. So notice in this scenario, we have a sample size. So we surveyed a total of 1,745 registered voters. 349 of them had the desired outcome of saying yes. So if we wanted the proportion, we would just divide. So this idea of a p-hat is something we already know how to do. It's just the vocabulary we're attaching to it makes it sound a little bit harder than it is sometimes. So what we're going to do is transition our example, from the p-hat calculations to an example involving Reese's Pieces. Now, if we were sitting in a seated section, we would do some activities with actually looking at some Reese's Pieces. We're going to do a little bit of background information and then look at another applet that provides a simulation for us. So if we were looking at a scoop of Reese's Pieces and we wanted to know which color, orange, brown, or yellow, had the greatest number, we would dump out a cup, get a scoop, and compare. Maybe I would give each of you a scoop and compare our scoops. So without looking at a scoop, it's kind of hard to make a judgment on this. But with most scoops, most students see that orange is usually the one that has the most frequent color or the highest proportion. So one thing I have students do is guess the proportion of each color in the bag. Again, without a cup of Reese's Pieces in front of you, we're kind of just taking a stab at it. You can do some Googling. There's some different values that people get, but we're going to investigate the proportions of each color, but specifically we're going to focus on orange in this case. So let's think about this question. If each of you had a sample of 10 Reese's Pieces, 10 pieces of candy, would you expect the same number of orange candies in their samples? In other words, would all 10 samples look identical? Most of you would probably say no, of course not. There's some variability within each sample. It doesn't make sense that you would expect exactly 4 orange or exactly 5 in each one. Do we expect to see some patterns? Sure. Now let's change this up a little bit and pretend that 10 students each take samples of 20 Reese's Pieces, so 20 pieces of candy in each cup. If I would ask you to write down the number of orange candies you might expect for these 10 samples, those number of oranges are going to be larger compared to the sample of size 10, because you would expect approximately maybe double the orange. Seems reasonable. But would you expect them all to be the same again? No, we're going to see some variability in the number of oranges between the 10 students' cups, even though we have 20 in each one. So some students may have 10 orange, some may have 8, 9, some might have 12. So we're going to see some variability. What we're going to do is go to the applet now and talk about some simulations. In our applet, we can look at two things, the number of orange and the proportion of orange. So for this applet, we're going to have a candy machine that's going to churn out a sample each time and then plot either the number of orange or the proportion. So I'm going to illustrate it, first of all, with the 10 number of candies in each sample. And for this probability of orange, this is based upon what we might know about the underlying distribution. Now, they've set 50% in this case. We're going to leave that. We don't actually know right now, without some background information, the true percent of orange. But most of the time, it turns out to be somewhere between 40 and 50% for a lot of the samples. So 50% for the population might seem reasonable. So I'm going to leave the number of orange checked, and then I'm going to draw a sample. Now, I will include the link for this so you can go back and take a look at it, just a website. So we churned out 10, we segmented orange and not orange, and we had 4 orange, and we drew that sample. So we could do it again. Notice I got 6, plotted that number, and I'm going to go ahead and up this to 5 samples at a time. Okay, so it animates it, plots. Notice it does all 5, and I think we're going to plot all 5. Now, what if I want to do a little bit more but not animate? Say I want to do 50 samples. Okay, build my distribution, 50 more. Okay. So notice what we start to see. If I do lots and lots of samples, kind of fill in the curve, and things start to look normal. But keep in mind, we only did 10 candies in each sample. Let's say I want to do 20. I'm going to go back to one sample, put 20 candies in each sample. And let's see, I'm actually going to animate that. And then we plotted 11. That first sample gave us 7. Now keep in mind before we had the option of between 0 and 10 orange candies. Now it looks like our graph, it only displays 2 through 18. Could we have 0 orange? Could we have 20? Sure, but those are pretty unlikely, so we've just chopped off part of our graph. So if we notice and compare those numbers, the numbers we're getting are larger because we expect to see more orange in a sample of 20. And let's see what happens. Let's do 50 samples at a time. We don't want to animate those, but we want to draw that sample. Notice if I plot 50 points, start to see something that looks normal. Start filling in our curve. Okay. Notice at this point we've done 302 samples. So what do we want to say in this case? Well, we've seen this idea of number of oranges and thinking about orange as success and anything else as failure in a different context. This is actually kind of a binomial. You're orange or not orange. Now, in this case, I haven't discussed the proportion down on the x-axis. I've only discussed the number of oranges. And this part ties in because the concept of number of oranges lends itself to a binomial distribution, success or failure with the oranges. And we did see that in chapter 6, under some conditions, the binomial distribution would be approximately normal. So we'll return to that. But let's see what happens if I ask us to look at the proportion. And I'm going to take it back to 10 candies at once. And let's just do 1 sample to start, and then we'll ramp it up. So same concept, generate 10 candies. 4 out of the 10 were orange, so my sample proportion, or my p-hat, is 0.4. Do it again. This time I got a p-hat of 0.6. Let's ramp it up to 50. Oops. Take off my animate and draw those samples. Now notice this isn't looking exactly normal yet. Maybe our conditions aren't going to be satisfied with these numbers. Just to illustrate what can happen. Let's say I change this to 20. And do 1 sample at a time. So I generate 20 candies. I have, it looks like 8 out of those 20, which gives me a p-hat of 0.4. Can plot that. Do it again, and then let's go ahead and do 50. So notice what happens. I have another distribution. It doesn't look exactly normal yet. I could plot some more and see what happens. This is looking better, maybe approximately normal. And what I want to show you is a comparison of the x-axis. When we were doing a sample of 10, you could still have anywhere from 0% or proportion of 0 orange to 100% or proportion of 1. The same thing holds true for a sample of size 20. In other words, one advantage is that our proportion is always going to be between 0 and 1 in either case.